Hi everyone, we are Team R. Ammonia is a commonly used chemical compound. This video will demonstrate an ammonia synthesis process which we designed. R-span is used to simulate the production process. We are going to include the process route review integrated with key simulation decisions, simulation results, and the energy analysis in the next few minutes.
The global model for this process includes purification of the LNG feed stream, removal and purification of carbon dioxide, ammonia synthesis and recovery. For the global thermodynamic model, the RKSBM model was chosen. This is due to the fact that it is well suited for processes involving mildly polar components such as hydrogen sulfide and ammonia or hydrocarbon systems. Furthermore, the RKSBM model is accurate and well suited for high temperature and pressure processes, which is the majority of the processes considered in this project.
Desulfurization. This step is vital as hydrogen sulfide can cause poison to catalysts used in the process. Starting from the absorption column, the feedstock introduction of an amine solution completely removes all hydrogen sulfide in the stream. The sweetened feedstock then leaves the top of the column to the NGL recovery section. The bottom stream then enters a stripper column, which allows for the recycled makeup of MDA. Elected RTL was chosen for the thermodynamic model as this process produces electrolytes, and this model is the most versatile electrolyte property which can handle both aqueous and mixed solvents. For the absorption column, it was modeled using step 2, as there isn't enough data to model chemical absorption on right frac, and this produces the closest results.
NGL recovery. This step involves the removal of hydrocarbons heavier than methane from the feedstock using cryogenic distillation and turbo expanders to ensure high purity methane. The column has a distillate temperature of -90 degrees Celsius and a bottom temperature of 47 degrees Celsius. The column pressure is 39 bar. Peng-Robinson was chosen as a thermodynamic model for this section as it allows for a good correlation for non-polar systems encountered in the petroleum industry. A shortcut distillation column DSCW was used for this step as it provides a good separation.
Primary and secondary reforming. The reforming stage is necessary since it generates the hydrogen required. The primary reforming unit operates at 780 degrees Celsius and 40 bar, whilst the secondary reforming unit operates at 1000 degrees Celsius and 40 bar with a nickel catalyst. A conversion of 99% of methane is achieved. The RKSBM thermodynamic model will be used since it is well suited for gas processes containing mildly polar or light gases. As kinetic data was not available and the reactions were at equilibrium, the RGIBS model was chosen for both reactors as it provides accurate results without the need for detailed stoichiometry.
Shift conversion. This step converts unreacted carbon monoxide to carbon dioxide to avoid the poisoning of catalysts using two reactors. The HTS is operated at 3.8 megapascals and a temperature of 350 degrees Celsius. The LTS is operated at 0.5 megapascals and 210 degrees Celsius. PRBM is used as RSK and PR do not give reliable results for the HTS. As connected data is not available and the reactions for the stage are at equilibrium, the RGIBS model was chosen for both reactors that provide accurate results without the need for detailed stoichiometry. Carbon dioxide removal. Similar to the desulfurization unit, this uses amine absorption. Through the use of a stripper, the MEA solution is then recycled. The absorption column operates at ambient condition and captures approximately 95% of the carbon dioxide present. Elected RTL property package is decided on for the thermodynamic model, and step 2 is used to model the absorption column. CO2 purification. To purify carbon dioxide, TAG dehydration is used to bring the water content down to 20 parts per million, as this is required for food-grade CO2. This involved the use of a stripper and the recycling of the water. Then, through the use of a distillation column which operates at 60 bar, the carbon dioxide is further purified. The bottom stream, which consists of food-grade carbon dioxide, flows at 20 degrees Celsius and 60 bar. A modified Peng-Robinson model was chosen as it accurately accounts for the interaction between polar and non-polar mixtures. A shortcut distillation column was used for this step as it provides a good separation.
Methanation.
To avoid catalyst poisoning, the remaining carbon dioxide and carbon monoxide will react with hydrogen to produce methane and water in a reactor which operates at 400 Kelvin and 34 bar. Peng-Robinson model was decided on compared to SRK as it produces more accurate results from mixtures that contain nitrogen and carbon dioxide. Ideally, R-plug would be used, but due to limited information, it was decided R-GIBS is the second best option, but the product of the reactor is to be specified to ensure no side reactions occur.
Ammonia synthesis. This is the most significant stage of the process, as in this stage is where the ammonia is generated. The reactor conditions are 375 degrees Celsius and 150 bar using a barium calcium amide catalyst with ruthenium nanoparticles. The RKSBM thermodynamic model will be used due to the same reasons mentioned previously. Likewise, for the reactor, an RGIBS reactor will be used due to the same reasons mentioned previously. Ammonia separation. The outlet stream of the Haber-Bosch reactor will be cooled down to 40 degrees Celsius and passed to a flash drum operating at 200 bar in order to recover the ammonia from this process. A flash drum model was used due to the fact that most literature sources and global chemical companies use this model to separate and purify ammonia. To purify the ammonia further to the minimum requirement, a DSTW distillation column model was used as this provides a very good separation result. Purge gas recovery system. The unreacted nitrogen and hydrogen will be recycled and a purge stream of 1% split fraction will be installed to prevent accumulation. The bottom stream of the flash drum will be passed through a silicon carbide membrane to recover 94% of argon and all of the remaining nitrogen and hydrogen from the main ammonia stream. Thereafter, this stream is passed through a copper anode palladium membrane at 350 degrees Celsius and 2 bar to recover all of the unreacted hydrogen. For all membrane processes, SEP2 model was used since Aspen does not have actual membrane models that could simulate gas membrane separations. The SRKBM thermodynamic model was chosen for the reasons mentioned previously.
Moving on to results. The simulation was executed on Aspen Plus and no errors or warnings were given.
The final process is using 695 kilotons of natural gas feedstock, of which 165 kilotons is sold after recovery. The main products are streams 47 and 77, which carry the carbon dioxide and ammonia products respectively. As can be seen, 1,023 kilotons of carbon dioxide is produced, as well as 673 kilotons of ammonia. Both streams meet their respective purity specifications, where ammonia is over 99.5% purity and carbon dioxide is over 99.99% purity.
Moving on to energy analysis. Out of the 34 streams that were possible to use for heat integration, 15 were used. All streams related to dehydration were not considered in process heat integration because this is usually undertaken within these units. The condensers in the ammonia separation and NGL recovery distillation columns were not considered due to the low temperatures required, suggesting heat integration would not be feasible to achieve these temperatures. The CO2 purification distillation column, reboiler and condenser duties were also not considered due to the small temperature changes. Finally, the two temperature shift reactors, the flash drum and the Haber-Bosch reactor were not considered due to a lack of temperature change. All hot streams chosen in the hotspot analysis and appraisal were included. Pinch analysis was used to perform heat integration and the following network was established. Heat exchangers above the pinch include H2C5, H2C2, H5C1. Heat exchangers below the pinch include H1C7, H2C3, and H2C4. The 6 heat exchangers used reduced the hot utility requirement by 10.2% and the cold utility requirement by 13.1%. The energy analysis yielded that heat integration can decrease total heating and cooling utility by 11.4%.
Although the energy savings may not seem significant, capital cost is reduced by minimizing the need for large duties from heaters and coolers, making the process more sustainable and self-sufficient. The heat integration could have been further optimized had it been possible to use the heat duties from the remaining hot streams below the pinch to heat up stream C2, but this will be inefficient due to C2's large heat flux. This explains the discrepancy between the ideal and actual heating and cooling requirements outlined in the tables. Thank you very much for listening.